Welcome. Previous class I have discussed about of the Diels Alder reactions. So previous class I have discussed about of the Diels Alder reactions. This also known as that 4+2 cycle addition reactions. Here what we have discussed that this is a one type of bimolecular reactions. Bio means that is two. So here what we say that two substrates are used. And what I have seen that the previous class I have discussed about of that substrates. The detailed things we have discussed. The substrate for Diels-Alder reactions. So what are the substrates? That is, one is diene. Okay, that is two double bonds are there. Diene, and another substrate is dienophiles. Okay, and for the dienes, what that condition that it must have two conjugate double bonds. Okay, not like it have 3, 4 or 1, 5 conjugate double bonds. Then this is not diene. Okay, so diene means that it must have the two conjugate double bonds. Okay, and dienophile means it must have one double bonds. Okay, so this is the dienes and this is for the dienophiles. Okay, so diene means that it must have two conjugate double bonds, and for the dienophiles it must have that one double bonds. So that things I have discussed. That also I have discussed that for the dienes, the substituents, if the substituents are electron donating groups, then the reactivity of dienes is increases. That things I have discussed in the previous class. So that's what I discussed here. For dienes, the substituents that is electron donating groups helps to increase the reactivity of diene. Similarly, for that dienophiles, electron withdrawing groups helps to increase the reactivity of dienophiles. So these things I have discussed in the previous class, reactivity of dienophiles. So now in this class, basically what I am going to talk is that about that MO orbital representation, that is molecular orbital representations of these Diels-Alder reactions. So today class I basically discuss about of that the molecular orbital representations of Diels-Alder reactions. Diels-Alder reactions or 4+2 cycle addition reactions. So today class topic is that the molecular orbital representation, that is MO representations of Diels-Alder reactions. So for that, basically what we know that the two substrates are there, and that two substrates, but if you give the heat, then we will get that Diels-Alder reactions product, that is let's say we have these substrates, dienes and dinophiles, then what will happen that they will go to a transition state. It means that this is going to be like this, and this will shifted to here, okay, and this is shifted to here, and this is going to be shift here. So this is positive, let's say negative, okay, this is positive and this is negative, this is positive and this is negative. It means that the transition state will form. So if I represent here, then see that this will going to form here, and whatever this is there, that is going to be here, okay, or I can do that here. This is going to be formed, and this is going to be that this, and here this is going to form, and this is going to be that living, and again this is going to form here, and this is also there. It means that it will do a concentrated mechanisms. It follows a concentrated mechanism, means that simultaneously bond form and bond break will happen. Here what we see that, see here that the formation is happening, here breaking, here formations, here breaking, here formations, here breaking, means that bond form, bond break, bond form, bond break, that type of that concentrated mechanisms will occur. This is the transition state, okay, this is the transition state. Now that here, then what will happen, that we will get the product, that means this, and here this bond has formed, and this was already there, sorry, this is already there, and so this has formed and this also formed, okay, and this has break. So this is the final products that we get, okay. So now this I did just by transition state, but now we look that how that MO approach, like you want to study that MO approach by molecular orbital representations, how these reactions will happen, okay. So by doing that molecular orbital representations, how these reactions will happen. So how that MO representations. So you see that for dienes, this is the diene, okay. Not that diene can be given, this is the diene, okay. For diene, sometimes this type of dienes will represent, okay. So variety types of dienes they will say, but we should keep in mind that that for dienes, that only one thing is fixed, that is that it must have two double bond in conjugations. Here what we see that here the number of carbon atom is 4, but here the number of carbon atom is 5, okay. Sometimes we see 7 like that, but the number of double bonds which are in conjugations, that is always 2, okay. So that's it has to keep in mind that. Why? Because of this for MO approach, this is very important, that for the dienes, that the not only MO approach, for whole that pericycle, this Diels-Alder reactions, that for the dienes this must have that two double bonds that has to be in conjugations. That's what we have discussed in the previous class, that if a ring, a benzene, that will not give that Diels-Alder reactions. Reason is that there the two double bonds are in the actually that two double bonds are not separated, because they are doing the conjugations with three double bonds, because we see that benzene rings, this is there, okay. So this is not, so the diene, reason is that this all are in the conjugation, so we are not getting the two double bonds. But if you take out of that plural, on this case, since that lone pair, here lone pair is there, but this lone pair is, since oxygen is highly electronegativity, so the electrons, the lone pair electrons are strongly bound by the oxygen. It means that these double bonds are freely available, and this is also in conjugations. So this shows that a diene characters, that's why this will do the Diels-Alder reactions, but this will not do the Diels-Alder reactions. That's what we have discussed. So important thing is that they should have that two double bonds in conjugations. Two double bonds, not 3, not 4, not 5. Okay, for diene it must have the two double bonds in conjugations. It should not must not have 1, 3, 5, dot 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 4 dot dot, that type of double bonds, double bond in conjugation. Okay, then it is not a diene. Diene means that diene stands for the two and in stands for the double bonds. Okay, so that means that it must have the two double bonds in conjugations for the dienes. Similarly, for the dienophiles means which loves the that diene. Okay, so that is known as the dienophiles. So for dienophiles we may see that this type of things. Sometimes this dienophiles, this is a dienophile. It means that it has that one double bonds, or sometimes we will able to see that this type of, okay, this type of things. So these all are dienophiles. Here we see that the double bonds, the conjugations here also presents. Okay, but that this is actually that electron withdrawing groups, that is the substituent. What I have said that for dienes, electron withdrawing groups increase the reactivity for the Diels-Alder reaction. So these are the electron withdrawing groups which increases the reactivity of the dienes. Okay, so dienophiles maybe this form is given, but that double bonds always one double bond is present. One double bond is present. Okay, that is for the dienophiles. So what we see that MO approach. So MO approach, what I'm going to say that this is the I'm taking this as the diene. Okay, and this is the dienophiles. This is the dienophiles. Now if I note that MO approach, then that molecular orbital representations of this diene will be that molecular representations. How will you do here? This one. So how many, count the number of carbon atoms? So 1, 2, 3 and 4. So 4 carbon atoms is present. So 4 carbon atom means 4 number of energy levels. It means that here I will do that 1, 2, 3 and 4. Okay, and let's say this is side 1, this is side 2 and this is side 3 and this is side 4, and that energy levels are, let's say 1, 2, 3 and 4. Okay, now this is important that now count the number of double bonds. So for dienes always 2 double bonds will be present. So 2 double bond means 4 pi electrons. So fill that 1, 2, 3, 4. Okay, this is on heating. Okay, this is on heating. So whatever the double bonds, if you just do that, then that is heating. Okay, now for the dienophiles, same things we will do. First count the number of carbon atoms. So 2 carbon atoms are there. So that's why I do that. This is psi 1 and this is psi 2. This is psi 1 and this is psi 2. Okay, now the energy levels 1 and 2. So now this is the important that now count the number of carbon atoms. So how many, count the number of double bonds. How many double bonds? So dienophile means always 1 double bonds. It means 2 pi electrons. Okay, so this is the representations, this dienes of this dienophile. Note that now the what I hear, these are the substrates. Substrates for Diels-Alder reactions. Okay, maybe the look that substrates may be this form, or that I'm looking that, let's say substrate is this form. Let's say substrate is this form. Okay, this is also dyne, and let's say dinopiles. This is also dinopiles. Okay, this is also dyne, this is dyne, and this is the dinopiles. For this, the MO representations will be, so you simply do here. So how many past is that? How many number of carbon atoms? That number of energy levels you will draw. So how many carbon atoms? 1, 2, 3, 4, and 5. So 5 carbon atoms. So 1, 2, 3, 4, and 5. Let's say this is psi 1, this is psi 2, this is psi 3, this is psi 4, and this is psi 5. Now the energy levels are same. This is 1, 2, 3, 4, and 5. This is on heating. Okay, so on heating, so now this is important that now count the number of carbon number of double bonds. How many double bonds? 2 double bonds. So I will fill that. But 4 pi electron, 2 double bond means 4 pi electrons. So 1, 2, 3, and 4. And for this case also, first our work is to count the number of carbon atoms. How many? 1, 2, 3, 4. So 4 number of carbon atom means 4 energy levels. That is this is psi 1, this is psi 2, this is psi 3, and this is psi 4. And so energy levels, let's say this is 1, 2, 3, and 4. So this is on fitting. And now the count the number of double bonds. Only 1 double bonds. This we will not count. This is for the electron withdrawing group substituent. This is the electron withdrawing group substituents. So this is the only the double bond. So how many pi electrons? That is 2 pi electrons. So this. So what is seen here, that either dyne is this form, the number of carbon atoms here increase, but that MO representation is same. It means that here also this, that psi 1 and psi 2. Oh, just here, just look that here. So which is the HOMO here? HOMO means highest occupied molecular orbital. It means that this is the HOMO. For this case, this is the HOMO. Okay, this HOMO, so this represented psi 2 is the HOMO. So same case for dinophiles. What you look for dinophiles? LUMO is look that I have discussed in the previous class. For dyne, HOMO is used to analyze the reactions. Okay, this is used to analyze reactions, and for dinophiles, LUMO is used to analyze reactions. So here for dinophiles, that LUMO you will look. So LUMO is here, which one? That is the lowest unoccupied molecular orbital. It means that this is the lowest and unoccupied. So this is the LUMO here. Or I can no. So this is the LUMO here. This is the LUMO. So it means that psi 2 is the LUMO. Okay. Now this is that like 4 carbon atoms, and here 2 carbon atoms is there for this substrate. Now if I take that this type of substrates, then still what we look that here also the LUMO is again that here what we look for dyne or HOMO, and HOMO means highest occupied molecular orbital. It means that again this is the HOMO. It means the psi 2 is HOMO. And for the dinophiles, we will look that LUMO, that is the lowest unoccupied molecular orbital. It means that this is the LUMO. It means that psi 2 is LUMO. So what we observe here, what we notice here, that is that even if I increase the number of carbon atoms for that substrates, then also what we see that for the heating, the HOMO and LUMO is remain same. Here HOMO is psi 2 and here LUMO is psi 2. And now if I increase the number of carbon atoms, if I change the substrates by increasing number of carbon atom, again we see that here side 2 is HOMO and here also side 2 is LUMO. It means that if I increase, so what we note that if we increase the number of carbon atoms for the substrate of substrates, that is diol or dinophiles of Diels-Alder reactions, there will be no change in frontier orbitals. Frontier orbital means HOMO or LUMO, but note that this is by heating. Okay, so we if we increase the number of carbon atoms for the substrate, that is diene and dinophiles of these Alder reactions, there will be no change in frontier orbitals HOMO or LUMO by heating. Okay, but now what I'm going to do that, now I will do that photochemical conditions. This is on heating, now I will do that photochemical conditions. If I give that photochemical conditions to it, then what will happen here? So you see that on photochemical conditions, so photochemical condition means that one electrons will shift to high energy states. Okay, so that's why I shifted here, and here also if I give that photochemical condition means that one electron will shift to that high energy state. So here again happening is that is going to be like this. Okay, so now in this case, which is the HOMO and which is the LUMO? So for this case, now that HOMO means highest occupied molecular orbital, it means that this is also occupied, this is occupied, but this is the highest. So now in this case, psi 3 is the HOMO. So on photochemical conditions, that psi 3 is become HOMO for this diene. Okay, and for that photochemical conditions, here that LUMO is again that is the psi 2, because the LUMO means lowest unoccupied molecular orbitals. It means that here vacancy is there, so one more electrons can come. So this psi 2 remain as the LUMO, because here still the vacancy, although one electron is shifted, but again here is vacancy is there, so one electrons can come to here. So this psi 2 is remain as LUMO for the case of the dinophiles. Even if here also if you look that, if you give that photochemical conditions, this 1 2 3 4 5, here also if I give the photochemical conditions 1 2 3 4. Okay, so if I give the photochemical conditions, then one electron will shifted to here, and here also that is there, and this shifted. So now in this case, by if I increase the number of carbon atoms, on that case what I see here, that here this is become the HOMO. HOMO means highest occupied molecular orbital, so psi 3 become the HOMO. Okay, same as that. So it means that increasing number of carbon atoms, that will not affect, either it may be heating or it may be photochemical conditions. So sorry, that is by heating or so that is not affected. Okay, by heating or photochemical conditions. Okay, it means that here also what we see, that this psi 3 is become HOMO, and for this also what we see, that LUMO means lowest unoccupied molecular orbital. It means that again here vacancy is there. One electron can come. So again this side is written as the LUMO. So even if you increase the number of carbon atoms, then also there is no effect in that HOMO and LUMO. That frontier orbitals will not get affected. Okay. So now what we look that this is the MO representation just I have did. Now that what we look that the interactions, how the bond will form. Okay. So for bond formations, or just we will write that. But from above what we notice that for by heating, that is if we give heat, then what we notice that side 2 is the HOMO. This is all right. For dyne case, side 2 is the HOMO, and for the dynophile case, again that side 2 is the LUMO. That we have seen here. Yes, so side 2 is the LUMO and side 2 is the HOMO for heating. And now if I will give the photochemical conditions, on photochemical conditions for this H nu. So for dyne, what we see here, so on photochemical conditions we see that side 3 is the HOMO. Okay, so photochemical conditions side 3 become the HOMO. And for that dynophiles, what we see that for dynophiles, so for dynophiles again that side 2 is remain as the LUMO here as well as also here, means that the increasing number of carbon atoms not affect the frontier orbitals. Okay, so that will not affect the, or you can write here shortcut that increasing the number of carbon atoms not affect frontier orbitals or Diels-Alder reactions. Okay, this one or this one. So here what we see that for heating that side 2 is the HOMO, and for dynophiles side 2 is the LUMO, and for photochemical conditions side 3 is HOMO, and for dynophiles what is that, that is again the side 2 is the LUMO. Okay, this is the LUMO because vacancy is there, still electrons can come. Okay, it means here side 2 is the LUMO. So that what we have noticed from this MO that molecular orbital representation, that's what we see here. Okay, this is the 1 and this is the 2, that is for heating and photochemical conditions. Now what we look that there are two type of interactions, means when the bond will forms, when the bond forming, that interactions are two types are there. Okay, types of interactions. So interactions, types of interactions for Diels-Alder reactions. So there are two types of interactions it have. One is suprafacial interactions, another is intrafacial interactions. Intrafacial interactions. So two types of interactions are possible. One is superficial interactions, another is intrafacial interactions. So superficial interactions means what is the superficial interactions? Here what you see that, let's say that we have that orbitals is like this, or let's say that terminal lobes, this is the terminal lobes. Okay, this is for the die, and terminal lobes, let's say psi even. Psi even means, why I am writing psi even? Even means that terminal lobes have different sign. Okay, so that's why I write that as psi even for the case of the, this is the for the time. Okay, so that means if it is psi even, then they have that different signs. It means that if it is positive, then this is negative. If it is positive, then it has to be negative, because this is that terminal lobes. I am representing about of the terminal lobes, because terminal lobes that will interact in the reactions. Okay, so this if this is positive, then this has to be that opposite signs, that negative, and this has to be positive. Okay, because we see that this dynophiles, this terminal lobes will do the interactions. Okay, so that's why we will represent these terminal lobes. And this, if it is positive and if it is negative, then this has to be negative, this has to be positive, and this has negative, because they will have the opposite signs. Okay, so that's why I represent the time in these directions. Okay, now for the dynophiles, what is there? Let's say that dynophile is this, and let's say this is also even. Now I am talking about of the, I'm by talking about of the even. Okay, so for this case, again we can represent this one. So here also that, since this is that, let's say psi even, then what you say that if it is positive and negative, then if it is positive, this has to be negative and this has to be the positive. Okay, this one, or we can represent that so that we can make the bonds. So we can say that, let's say this is negative and this is positive, then this will has to be opposite to that, that means positive, and this is negative. Now if you make the bonds here, then what will happen, that this lobes and this lobes have the same sign, means interactions is possible, and this lobes and this lobes have the same sign, so interactions is possible. So if this type of interactions, means if they have that this that lower lobes and this upper lobes have the same sign, means that the interactions will possible. So if these things is happening, then this is called, here that bond formations is possible, bond formations occur, and this type of interactions is called that suprafacial interactions. Suprafacial interactions. Okay, and likewise that if it is that psi out, let's say if it is the psi out, if it is psi out, means they have that same sign. So for that case, what is, look here, this, and if it is positive and if it negative, then this also has to be positive and this also has to be negative. This is for the, let's say for the dyne, and for the dynophiles, okay, so here, so if this is also odd, then this will be positive and this will be negative, or we can write this one so that we can make bonds. So we can write this negative, then this positive, then this also has to be negative, this is positive, so that interactions is possible. So this is also again the superficial interactions. Now the question is that, then which is that intrafacial interactions? So intrafacial interactions means that where the bond formation is not possible. So for that case, let's say that if I talk about of this psi even, and for the dyne case, let's say it has this type of interact, this is that, and let's say it is positive and this is negative, then since this is even number, so there has to be opposite, then this is negative and this is positive. Okay, now for the dynophiles, the terminal lobes I can draw here. So note that these are the terminal lobes. Okay, this is the terminal lobe, this is also another terminal lobes, another terminal lobe of dyno. Okay, so now the for dynophiles again that is like this. Okay, now if it is let's say, so since this is even, so they have that opposite sign. So if I'm writing here negative and if I write it positive, so if you make anyway, means this is negative and this is positive, and since this is the even, so they should have that opposite signs. It means that this should have that positive and this should have that negative. Okay, so now if you make the bonds, here bond formation is possible. Okay, so let's say this is positive and negative, and this negative and this is positive. And positive, then this is has to be the positive and negative. Then here interactions is possible and here interactions is also possible. Okay, just a minute, I didn't think wrong. Okay, what you see that, then this is become that suprafacial interactions, but what you see here that is, so if it is positive and this has to be negative and this negative the positive. Okay, now if it is positive and if it is negative, and then it has to be negative and it has to be the positive because they have the opposite lobes. So what we see here, something getting wrong here, just a minute. Okay. So yes. Okay. So if it is even and it is also even, this dynophile, this is also even, then this will do what? It has to, so this the orientation, we will do that possible orientations. Okay, so it means that if it's positive negative, then let's say this is negative and this is positive, then this has to be positive and this has to be negative. Now the interactions is possible. So if it is psi even and this is also psi even, and let's say if it is 2 and if it is 2, okay, on that times or what you see that, let's say here we have that psi odd, okay, or any values, and if it is negative and this is positives, and let's say, so let's say if it is positive and negatives, on this case what we see that although here the interactions is possible, but here the interactions is not, here interactions is not happen, so here no interactions, here only the interactions is happened, interactions happen. It means that one lobe is doing interactions and another lobe is not doing interactions. That type of interactions is called that intrafacial interactions. Intrafacial interactions. Okay, so it will more clear when we take these examples. Okay, now I will take these examples. We know that what do we mean by suprafacial interactions and what do we mean by intrafacial interactions. Here that bond formations is possible, bond formations occur here that no bond formations, no bond formations occur. Okay, so that superficial interactions means that where that both cases that the interactions is happening, that this negative, this lower lobes and this above lobes doing the interactions and this distributed. So where that both the cases that interactions happening, that type of interactions called superficial interactions. Here that bond formation is possible. And whereas for interfacial interactions, what you say that one will be doing that, one will be the interactions happening, but over this no interactions is happening. On this case, that type of interactions is called interfacial interactions. Here no bond formations is occur, no bond formations. Okay, so this is the interfacial and superficial interactions. Now we will take that example, we will take our what we have get from here. So this one we observe that side to is homo for heating what we seen, and for photochemical what we have seen. Okay, I can erase it. Okay, let's do this example. So anyway, that's fine. So for the heating, what we see that is that diene case, sorry, heating. So diene case side to is homo, and for dienophile side to is homo. Okay, so that's now for heating what I'm doing that representations. Hmm. Okay, okay, it's fine. So what is seen here? Sorry about that. Okay, so sorry for the disturbance. So what is seen here, that is for the heating. So for heating, what is seen, that if it is heating, then what is seen, that side 2 is the HOMO and side 2 is the LUMO. Okay, so that is on heating. What is seen here, the for dyne, that is also side 2 is HOMO and dynapile also side 2 is the LUMO. Okay, this is for the dyne and this is for the dynaphiles. So if we do that representations, then what you see, that for the dynes, let's say this is that the terminal lobes. Okay, and this is, since this is that even number, so what is in that, this is the, if it is positive and negative, then this has to be negative and this is positive, because this is the even number, they have the opposite signs. Okay, this is for dyne case. Now for the dynaphiles, here the dynapile side 2 is the HOMO, and for dynapile also, what is that, side 2, that is the LUMO. It means that here also that representations is like this. So here also what you see, that if it is negatives, then it will be positive, then that, since this is the even number, so opposite, so it is positive, then this is negative. Okay, because they will have the opposite signs. So what we see, that interactions here happen is, so both the cases interactions happen negative negative, positive positive. So this is called that suprafacial interactions. Suprafacial interactions. It means that bond formations will happen. Bond formations, or I can say that bond form. Okay, so this is the case for that, as if that both are on the heating conditions. Okay, this is on heating. Now if I look for the photochemical conditions, let's look for the photochemical conditions. For photochemical conditions, that is H nu. What we seen, that for the dyne case, so for photochemical condition, dyne case side 3 is the HOMO. Okay, for dyne case what we see that side 3 is the HOMO, and for dienophile case what we see that the side 2 is the LUMO. Here side 2 again, that is the LUMO at photochemical conditions, so that's we will write here dienophiles, again that side 2 is the LUMO. It means that if you do the interactions here, then what we see that let's say that for the diene case, for the diene, if it is that like that opposite lobes are this, and since this is the side 3 means that, or it means that they have that same that terminal lobes have that same sign. It means positive, then this is also positive and this is negative. And for the dienophiles, what we see that this is the side 2, it means that even number, it is side 2 is the LUMO here, and this is the HOMO here. So that means that this is the even number. It means one is positive, let's say this is negative, this is positive, then this also will be the positive and negative, because this is the even number, they have that opposite signs. So now if you look the interactions, then here the interaction is possible, but here the interaction is not possible. It means that this is the intrafacial interactions. So intrafacial interactions means no bond formations will occur, means no bond form. That's why what we see that from here what we discuss that whatever if you increase the number of carbon atoms, then also that MO orbital representations for the diene and dienophiles is remain same. It means that for the whole Diels-Alder reactions at photochemical conditions, never that Diels-Alder reactions will happen. So from here what we notice that in photochemical conditions, what we see that intrafacial interaction is happening. Intrafacial interactions occur, means that no bond form, so in photochemical conditions. So from here what is said that Diels-Alder reactions not happen in photochemical conditions. Okay, so Diels-Alder reactions, but what we see in that in heating, what we see that superficial interactions, it means that bond has formed. So Diels-Alder reactions is happen on heating. Okay, so this is what we see that from this molecular orbital representations. So this is the molecular orbital representations for Diels-Alder reactions. So next topic is the stereochemistry. Stereochemistry of Diels-Alder reactions. Okay, so what it says that this part is very important in that CSIR NET and GATE point of view. So what the things we will see that what are the substrates for the Diels-Alder reactions? One is diene. So dienes can be, what I say that this, and this also makes this is the diene. Okay, this is also the two double bonds are in the conjugation, so this is the diene here. Now the dienophiles is This one also we can say the dinophiles. It means okay, and here let's say we have this type of electron withdrawing groups. This is the dinophiles. Now questions will come that if you are doing this, then here we will get the one the products. The stereo will be different stereo difference. I can say product with one stereochemistry, one stereo, and another is that the dyne is same. This is the dynes, but now that I will actually reverse it. Suppose that I will make that oxygens here and this one, and what I do here, this case, okay, means I just reverse it, then that product with different stereo will form. Product with different stereo. It means that if you change, dyne will be same, but if you change the dinophiles, then the product will get some other stereo. Here we will get product with one stereo, here we will get product with some other stereo chemistry. Okay, product with other stereo. So that's what is you will look that about of the stereochemistry of the Diels-Alder reactions. So if we change the orientations of the dinophiles, that wise we can get the different stereo. So that's we say that sometimes exo product, sometimes the endo product. So what you see that if it is this orientations, then what you see that here we will get that exo product that we will see now, and if it is like this, then we will get that endo product. Okay, so and what we see that this exo product is that thermodynamically controlled, means thermodynamic products, not controlled, thermodynamic product, and this is the kinetic product. And what we see that this kinetic product, that intermediate, that the sorry, not intermediate, that transition state is more stable. Here that transition state is more stable. It means that this is the stable product and this is the less stable products. So that we will do now. So okay, so let's do first case. Let's talk about that exo product. Or first to go through the endo products. Endo product. Okay, so here what we see that this is the dyne will be same. This is the dynes, and dinophiles will be that is this will be the dinophiles. This is the dinophiles, and this will give the endo product. How it will happen? So how the reactions will happen? So if you move the electrons here, then see that this is the primary interactions, means here and here, this and this bonds, and this bond will do the interactions. What you see that here if we see positive and repeat negative, then this is going to move and this is going to move. Okay, this is positive and this is negative. So actually where the bond form, new bond will form, that new bond formations will occur here and here. Okay, similarly what we see here, that if it's coming, then that is going to rotate here. it means that let's say that it is positive and this is negative, so bond formations will occur here, here and here. It means that these positions and this position, these are the prime what you say that these are the primary interactions, means that these interactions must be present, means this here actually the bond formation will occur. Okay, that I can say that here new bond going to form, here new bond going to form. Okay, here new bond going to form. So how the interactions will happen? So that's what we see here, that is going to be that this, and this is rotated to here, this comes, and here that bond will form with this, so that bonds, so here that new bond will be here, and this again goes to here, and this is the makes the new bonds. Okay, so this is formed and this is going to like that, and that bond is formed. Or if you get confused, then just number it. It means that this is 1 and this is 2 and this is 3. Okay, and this is 4 and this is 5 and this is 6. So same things here, this is 1, this is 2, this is 3, this is 4, and this is 5 and this is 6. Now here what things are there at 1 and 4, 1 and 4 this is there, so that we can draw here by like this. Okay, and here 5 and 6, this whole thing is there, so that we can draw like this here, and oxygens here and this. So this one I simply write it, but now actually that stereo, how will we write it? So this one we can make this type of bonds, that means this bonds we can make here, and this is the dot. So just name it. If you get confused, then just name it. That is 1, let's say 1 and 2, 3, 4, 5 and 6. So at 2, 3 double bonds are there, make 2, 3 double bonds, and 1, 4 that is there, so make that, and 6 and 5 we have this. Now what we see, that exo product and endo product. Okay, so since we are going for that endo products, this is the endo product. So endo product means we know that this is the axial and this is the endo. Endo means this will come to the endo product, means endo side like this. Okay, because this is the exo and endo is this, so we will make that things here, and this also coming to like this, and here we have that oxygen. So and here we will that hydrogen. This is the exo, this is the exo sides, and this is the endo side. So our group will be on the endo side, that's why this is called that endo product. This is our groups, this is the bulky groups, and this is the what this groups, this group has come to the endos, that's why this is called that endo product. Okay, now how will be the exo products? So exo product is that same though, so here also same things will form, except that exo product means this will go to the above side. It means that is going to be like this. Okay, and this is going to be like this, and here we have exo product means this is the exo, means that C double bond will come here, and this is going to be double bond like this and this, and that hydrogens will be in the axial sides. This will be the on the endo side. So this is called the exo product, because our groups is this is on the axial side. Okay, and this exo product is less stable than endo products. Why? That we want to discuss here. Okay, so we are discussing about that endo products. So end product, if I do that molecular orbital representations, then how will you do that? Let's say our that will be like this. This is that this is the for the time, okay, and these are the uh, where the bond formations will occur. Okay, this is the terminal lobes. These are the terminal lobes, and they have that, let's say, this type of bond, orbitals. Okay, and here also orbitals are there. And what we see that, since that we see that this is the side 2 for the diene, side 2 is the HOMO on heating, because heating that reactions will happen. It will not happen at photochemical condition. So whenever we discuss about of Diels Alder reactions, we always discuss on heating. We will not discuss about of the photochemical conditions. Okay. So this is side 2, that is HOMO. So side 2 means this is even. It means that they have the opposite lobes. This positive and negative. Then this should be negative and this should be positive. And what we see that in side 2 means one node is there. It means that here one node you have to make. Okay, this one and this one is same. So one node you will make. It means that a positive and negative, then this has to be the negative, so that we can make the nodes. Okay, this will be the negative, then this is the positive. Similarly, this is the one nodes we have to make, and so this is going to be the positive and this is going to be negative, so that one node will form. Okay, so this is the orbital representations for the diene. And for the dienophiles, so what you see, that diene is always same things. Okay, now if the dienophiles, so dienophiles for end product, what you see that oxygen will be here, and this is going to be like this, and we have this one, and we have this one. Here we have this groups, here we have this groups, this. Okay, for this interaction, this is the if this is happening, then this is the for the indo. Okay, and if this dienophile is like this orientations, let's say this is going to be like this, and this is there, and this is there, and this, then this is called that exo product. Here exo product will happen. Okay, so now what we see that or what we see that here also that LUMO is side 2. Okay, now if you do that orbital representations for these molecules, then what we see that the side 2 is LUMO, means that that first we look that where actually the bond form. So bond form will occur to this one. Okay, this one. So this one first, our intention is that first to form that, which actually it's better to mention it with other colors, where actually the bond formations will happen. So I like to mention it by, okay, and here, so these are the where the bond will form. Okay, so if this is the side 2 and this is the event, so this is also again have that that is opposite signs will be there. It means that if it is negative and if it is positive, then this has to be positive and this has to be the negative, because they have the terminal lobes should have the different signs. Okay, now here again the bond formations will occur. Actually bond form here. Okay, here bond form will not occur. Okay, actual bond form here it will occur. Similarly, actual bond form here it will occur, here not will occur. Okay, so that we has to be keep in mind. Okay, so this is the primary interact, means that where the bond actually form, and this, since this is the side 2 and LUMO, it means that the opposite the terminal lobes have the different sign. It means if it is negatives, then this has to be positive. So this is negative positive, then this has to be positive and this has to be negative, because they have the different lobes. Okay, now these are the secondary interactions. These are the secondary interactions. That's I can do. These are the secondary interactions. Okay, these are the secondary interactions. These are the where the bond actually not forming. Okay, these are the secondary interactions. And that hello lines that I mentioned, hello lobes, shows that where actually bond formed. Okay, must needed interactions. And this I will do this. And that white lobes I've done that. These are that not so important interactions. So you understand that this hello lobes, these are the must be that has to do the interactions to the bond form, because the bond formation is happening for endo and exo, both are bond forming. So it means that they should be do the interactions. So this has to do the interactions. Okay, this is the for case, for this case here, that will form that endo product. Here you will get that exo product. Okay. So what is seen here, that now we look the interactions. So these negatives and this negative will do the interactions, but before that this also interactions is possible. It means that this secondary lobes, what you see, that means that here that they should not do the one node should be needed, because it's the side 2 has the one node. So here I has to put negative, here I has to put the negative and positives. Okay, and here I will put that negative and here I will put the positive, so that there should be one node here. Okay, so now before doing these interactions, this again this is available, so this also can do the interactions here. It means that I can do the interactions here also, and here also interactions happen. So before going to the past interaction, this interactions also easily available. Okay, this must be done, these interactions must be done, these interactions, this hello interactions must be done, but these interactions also available. Okay, but in the case of that exo product, what will do that this hello will be this is going to do the interactions with this is going to interactions with this, and this is going to interactions with this, but this is negative and this is positive, and this is positive and this is negative. So but so this primary interactions is easily available, so it will not go to that secondary interactions. But for this case, before primary interactions, the secondary interactions is easily available, so both interactions will be happen. But in this case, what will happen, that partially it will available the primary interaction, so it will not go to the secondary interaction. It means that in the end of product cases, that primary interactions is happen, that will definitely will do. Primary interaction is where the bond formations will occur. Okay, and secondary interaction also happening here, means where that where bond formation not happening, but that interactions is possible. So second interactions is also possible. It means that two interactions happen, but in this case only primary interactions will happen. Primary interactions. So what we say, that here we will get that only one interactions we are getting. Here, sorry, here we are getting that two interactions. Here we are getting that one interactions. Only one interactions is happening. So now we will say that here two interactions, here only one interaction. So now we will easily say that this end of product, the transition state is more stable, because of here two interactions happen. So this is more stable, and this becomes the less stable. Reason is that here only one interactions. Now the question is that why here one interactions, why here two interactions? So that it will get confused. Then what we say, that here we see that before going to the primary interaction, secondary interaction is available. So it will do secondary interactions, then it will go to the primary interactions. But for the case of exo product, firstly it is getting that primary interactions. So if already bond has 4, then it will not go to the secondary interactions. That's why here only one interactions will happen. But here that before bond form, one interaction is happen. So these interactions also do, and this primary interaction that definitely it has to do. It means that before forming a bond, it will do the secondary interactions. It means that 2 interactions will happen here. So that's why this transition state is more stable. But in this case, it directly getting the primary interaction. Already bond is 4, so it will not go to the secondary interactions. That's why here only one interaction is possible. So since one interaction is happening, that's why this is the less stable and this is the more stable. Okay, that's why end product is more stable, stable than the exo product. And end product is actually what? This is the kinetic product. Kinetic product, and this is the thermodynamic product. Thermodynamic product. And actually thermodynamic product happens if you give that more heat. So it happens more heat required for thermodynamic product. For kinetic product, low temperature, that the low temperature required. So at low temperature also that kinetic product will happen, and that is the end product. Okay. So today after this we will discuss more in the next class. We will basically discuss about of the stereochemistry of that molecules, and we will look the different questions that we will discuss in the next class. Okay, so today after this we will discuss more in the next class. Thank you for today.